Welcome to the next video in abstract linear algebra. This is video 5 on vector spaces. It corresponds to chapter 1, section B of the textbook. So let's start with some examples of vector spaces. You'll kind of detect a pattern and then I'll give the official definition. So the most familiar vector spaces are lists of real numbers, right? So we could take a list of real numbers like the list 1, 2, and another list like 3, 1. And if you take the set of all such lists of 2 real numbers, that forms a vector space. And we have in this diagram kind of a picture of what actually really makes it a vector space, which is the fact, well, for one thing, right, this isn't everything, but for one thing, you can add vectors together, right? That's part of what it is to be a vector space. Here I've drawn a diagram where the vectors obey this kind of parallelogram rule that hopefully is familiar from a previous linear algebra class. But in any case, the point is, part of what it is to be a vector space is that it makes sense to add some 2 vectors together. Moreover, you can also scalar multiply a vector by some element of a field. In this case, we could take a given vector of 2 real numbers, multiply by a real number, and that makes sense, right? For this kind of situation, we would diagram it by sort of, if we multiply by 2, we would double the vector or something like that. But in any case, these are sort of defining features of what it is to be a vector space. It is possible to take some 2 vectors and add them together. That makes sense in a vector space. Also, if you take the scalar field, right, if you take a scalar, something out of the field, and you multiply by the vector, that makes sense also. So those are important, defining features of a vector space. Also, the plus and the scalar multiplication operations should, in some sense, behave as you would expect. Now, what it means to behave as you would expect is exactly what we're going to iron out when we give the formal definition of a vector space. But, right, there should be some sense that, the addition should be associative, right? So if I take 3 vectors, right, if I've got vector A plus vector B plus vector C, if I put parentheses around like this, you should get the same thing if you put parentheses around like that instead. That's associativity. Hopefully that idea is familiar from a previous course. And so that's like a property that's behavior as we would expect vector addition to obey or something. So that's one example of a vector space. Let's look at another very important example of a vector space. Now, it's not going to be super important throughout this class. It's just important throughout mathematics. The example is the space of all real-valued functions of a real variable, right? So the domain is the reals, the range is the reals. It makes sense to add any 2 such functions. So that's good, right? That's part of what we need to have a vector space. It also makes sense that, to multiply by some real number. So it's got those 2 important, so to speak, operations. The scalar multiplication might not really count as an operation technically. We'll get into that later. But in any case, right, we've got the plus and the scalar multiplication. They make sense. And when we get around to saying exactly what this means, we will confirm that indeed their behavior is what we would expect. So that's another example of a vector space. There are many non-examples of vector spaces. So for one thing, if we just took the set A, B, C, and especially if we think of them as like strings, then what would we choose for plus and for scalar times? Well, nothing stands out, right? We have no natural, thing that we would choose for this, and probably there just is no good choice that would turn this into a vector space. But the important point here is just I'm kind of demonstrating that this is not a vector space by just kind of pointing out that it doesn't have a plus and a times, at least not one that comes to mind readily. Here's another example, the set of all matrices. Again, this one does not have a natural plus and times. And here the reason is that if you took a 2 by 3 matrix and a 4 by 7 matrix, you can't add those together in the normal way of defining matrix addition. I mean, maybe you could find some kind of super funky, weird definition of matrix addition where that is possible. But with our familiar notions of plus and times, these are non-examples. You can't add or scalar multiply. Well, I guess with the matrices you can scalar multiply, but you can't add. Okay, but let's, rather than simply lacking in operation, let's look at something that's a little more robust of a non-example. And let's talk about this set here. So it's the set of all lists of two real numbers, but they have to be non-negative real numbers. Now, I claim this is not a vector space. Why would it not be a vector space? Well, it does have a plus. It does have a scalar multiplication, so it passes those two tests. And the plus operation is associative, right? If you take 3 vectors and add them all together, it doesn't matter where you place the parentheses, right? So that's got that nice behavior of vector addition. It's got all the other kind of nice properties of vector addition. It's got commutativity, right? So if you took So if you took a vector v plus w in this set, it would get you the same thing if you did w plus v. So it satisfies commutativity, which is going to turn out to be another one of those behave as you would expect properties for vector addition. So it satisfies that. So what's it missing, right? What's the thing that this example doesn't have? Well, it's closure under scalars, right? If you took, for instance, the vector 1, 1, which certainly is in this set. Let's call this set X just for easy reference. So this example vector is in the set X, but if you multiply by -1, right, and that is an element in our scalar field, right? Presumably, if we're taking lists of real numbers, then our scalar field is the real numbers, or even here I just say that we're taking the scalar field to be the real numbers. Well, then that's a real number, and I should be free to multiply by it. But if we multiply that out, we get this, and it is not in the set, right? So that means that this set is not closed under the scalar multiplication. That's the kind of thing that we would say is like, does not behave as you would expect. So that's also a non-example of a vector space. Okay, let's finally get around to the official definition. So we have to have a set, perhaps we should even specify a non-empty set. And we'll have to have a field. It won't matter which one, so we're just going to call it F, right? An abstract field that could typically refer to either the reals or the complex numbers. We have to have some two functions. Now, the first one, written with the plus symbol, is actually going to be an operation. This is actually going to be a requirement, right? You should be able to input some two vectors, and it should output a vector. So that's an operation. Notice that this implicitly means that we're talking about an operation for which v is closed under the operation, because we are requiring that the values of the function should be v, right? So that is effectively the same thing as requiring closure for the plus operation. Also, we're going to have another operation. This is going to be our scalar multiplication. I'm going to write it with a dot. It should have domain, the scalars, right? F here is the scalar field. V is what will eventually be our vector, our set of vectors. So if you take a scalar times a vector, you should get another vector. So this, right, because I am, defining the domain and range in this way, this again is essentially the same thing as the property of closure under scalar multiplications, because we are requiring that the values of the function are in v. So that's effectively the same thing as closure. The first function we call addition. The second, right, that's the one written with the plus sign, of course, right, and that can be, called plus, it can be called addition. The second one is multiplication, specifically scalar multiplication. Okay, so we've just got our raw components at this point, right? We've got a set V, non-empty set V, a scalar field, a plus function, a times function, and now we're going to say that this is all an example, or these objects are a vector space if they satisfy the following three properties. The first property, it has everything to do with plus, right? A bunch of properties we require of specifically plus. And the first property is, as we've discussed, it must be associative. So we've already talked about that. It also must be commutative. We've mentioned that before. It must have an identity. So this would be the zero vector in the vector space, right? So there must exist this identity element. And if you've never heard, this sort of vocabulary before, what does it mean to have an identity element? It means that if you take any other vector in your set of vectors, then the following equation is satisfied. That if you add 0 to it, then it shouldn't matter in which order it goes. I mean, of course it doesn't matter because we're assuming this thing is commutative, but anyway, adding it on either side does not change the vector, right? This is the property that defines what we mean by an identity element. So this is what an identity is. We often write the identity of the vector space with the number 0. I always like to put arrows on top of my vectors. But the point is that we are guaranteed, it is a property of vector spaces that this 0 vector must be in there somewhere. So that's what this part means, is that the vector space must have an identity element, namely the 0 vector, and it must have inverses. Now, when I say that, I mean an additive inverse. So what I'm saying is that if you take some vector v in your vector space, then its inverse, right, negative v, must also be in the vector space. And what is this, right? Now, I think we all kind of intuitively, instinctively know what it is, but formally, negative v means... It means that element which, when added to V, results in the identity, right? So that is the official definition of the inverse element for V. And so when we say that the collection has inverses, what I mean by that is every V, right? Every vector in your set V has some corresponding inverse element also in V. So, by the way, this is exactly what didn't happen with our previous example, right? If you let your vectors of two real numbers be any real numbers, then the negative vector, right? So that's, what we'd be talking about here. Turns out, right, that's the same thing as just taking negative A, negative B. And so that always exists, right? Because this is a real number, this is a real number, so this again is in the set of lists of two real numbers. So if you allow all lists of two real numbers, then that has inverses. But this is exactly what doesn't happen if you require the coordinates to be non-negative, right? So that's why that example failed, is because it wasn't closed under inverses. Another way to see it, right, because it's somewhat equivalent, is that it wasn't closed under scalar multiplication. So even there, we could have said, well, it fails this property also, in a way, because of how negatives work here, it kind of failed on both accounts, right? It both fails to have inverses, and it failed closure from before. But anyway. So those are all the properties that we require of addition. And so the next collection of, or really the next requirement property of a vector space is for the multiplication operation. And here what we're saying is that the scalar 1 is a multiplication identity. So what do I mean by that? What I mean by that is that if you take any vector in your vector space, then computing 1 times the vector v gets you the vector v. So that's what it means to be an identity for multiplication, for scalar multiplication, is that, again, right, it kind of leaves the vector unchanged. So we require this for any vector space. And finally, we get kind of two similar but not exactly the same distribution laws. We say that multiplication distributes over, I should have said vector plus and scalar plus. So let's talk about what it means for multiplication to distribute over vector plus. That would be the feature that if you take any scalar, I'll call it A. Let's go ahead and say A is a scalar element, and we'll take V to be, or V and W to be some two vectors. Then, if you multiply A times V plus W like that, you get distribution over the vector plus, right? That's the vector plus. And so we get distribution over the vector plus, so that means that we get AV plus AW. So that's distribution, right? That's scalar multiplication, this right here. By the way, sometimes we write the multiplication symbol, sometimes we drop it, right? Just out of like laziness. We know that if you just have things concatenated together, then that means multiplication. But in any case, so that is distribution over vector plus. Then we've also got distribution over scalar plus. And that's this very similar but technically slightly different requirement that if you do the plus operation in the field this time, right? This is not the vector addition, that's the scalar addition. And so if you have two scalars plus each other, and the whole thing is multiplying a vector, then the vector can distribute into the scalar sum, right? So that's multiplication distributing over the scalar sum. By the way, just as a matter of notation, although we'll tend to write, the scalars on the left and the vectors on the right, and that's kind of what is required by what we said for our domain over here, we'll kind of understand that if we ever write, and I'm sure this will happen from time to time, if we ever write VA like that, right, a vector on the left and a scalar on the right, just understand that that's just kind of notation that sometimes just happens to us. But really just means exactly the same thing as putting the scalar on the left, right? So we might write it on the right, but if we're being very official and very formal, then we would say, well, what I mean is for it to be on the left. And so anyway, so just understand that this is just notation for that. Okay. Okay, as a final point about some vocabulary, if we know that we have a vector space, right? So if it is given that V and F satisfy all those conditions that make it a vector space, then anything inside of V we call a vector, or we might equivalently call it a point. So those are just two perfect synonyms. There's no difference between them. They're just elements of a vector space. And the elements of the field we call scalars. I've been talking like this for a while now, and I hope that has made sense while I was doing that, but we're now just kind of like making those definitions official. That vectors are simply elements of something that satisfies the vector space properties. Scalars are things that satisfy the field part of the vector space properties. Okay, also, if the field happens to be R, then we call this a real vector space. And if the field happens to be C, then we call it a complex vector space. And also, we use V dot S dot as an abbreviation for vector space. Okay, let's end on two slightly more exotic examples. We saw familiar ones just to build some intuitions, but now that we actually have the formal definition, let's see how technically these slightly stranger examples actually technically qualify as vector spaces. So we know that we can take lists, finite lists of real numbers, right? We can talk about R2, or we could talk about C7, or any other such, lists of field elements, finite lists of field elements, and we know that those are vector spaces. But it turns out that finiteness is not necessarily required. We can also take infinite lists of field elements, right? So we could take this, what is effectively an infinite sequence of elements from whatever this field is, and if you form this collection, and we'll also have to say what we mean by plus. So what do we mean by plus when we're talking about infinite lists? Well, it's just kind of natural and obvious, really, right? We'll just do coordinate-wise addition. So if you have the list x1, x2, and so on, and we add another list y1, y2, and so on, then this is what we mean by their addition, right? You just do coordinate-wise addition, right? Take the first coordinate of each list and add them together. Then take the second coordinate of each list and add them together. And that builds up your new infinite list of field elements, right? That's a field element because it's the sum of two field elements. That's another one, and so on. So that tells us that this is another element of the collection of these, infinite lists of field elements. And I say that because that's, part of confirming that plus, right, we have closure under addition, right? You take two infinite lists of field elements, add them together, what do you get? Another infinite list of field elements, so it's closed under addition. You can similarly define scalar multiplication. So if you have any particular element from your field, then so if you take a field element together with a vector from the vector space, right, so that's taken out of the infinite lists of field elements, then what do we mean by scalar multiplication? Well, again, it's coordinate-wise, right? You take this scalar and you multiply by the first coordinate, and then you multiply by the second coordinate, and so on. Again, this is a field element because it's a field element times a field element, right? And fields are closed under their multiplication, right? This next one is again a field element, and so on. So you again get an infinite list of field elements, and that is why this operation is closed under, or that's why this example is closed under scalar multiplication. And you can go so on, right? I'm not going to go through confirming all of the other properties that make this a vector space, but you can check them. In fact, it is a good exercise, and I invite you to do exactly that. So go ahead and check that the plus operation is associative, commutative. What else do we need? It has an identity. You should go ahead and think. Actually, let's do a little fun game. Think right now. What is the identity element for this vector space? I'll give you a countdown to 5. Pause the video if you need longer. 1, 2, 3, 4, 5. What is it? It's the list of all zeros, right? The infinite list of zeros. That's the identity element in this example, right? So it has an identity, and you can prove that that's an identity. Okay, what else? It means everything has to have an inverse. I'll let you check that on your own. So on and so on with the other properties that make this a vector space, but I promise you it is a vector space, and I encourage you to check it formally for yourself. Okay, let's move on to the next and final example. Now, this initial part is true whether we're dealing with vector spaces or not, right? If we have any two sets, x and y, and we write x to the y, what we mean by all that is the set of functions from y to x. So that's what this notation just means. Now, let me try to explain quickly why we do the notation like that. Well, think about what we get when we have 1, 2 in the bottom, right, in the base, and let's say that we've got 3, 4, 5 in the exponent. And we're talking about all possible functions from 3, 4, 5, right? So we could say that that's 3, 4, 5 to the set 1, 2. So there's 1, there's 2. And then let's count up how many such functions are there. Well, we could send 3 to 1, or we could send it to 2, right? We could send 4 to 1, we could send it to 2, right? We could send 5 to 1, we could send 5 to 2. So what that means is that how many such functions are there? Well, there are 2 choices for where we send 3. There are 2 choices for where we send 4, 2 choices for where we send 5. Altogether, there are 2 to the 3 possible functions, right? You multiply all the choices, and that gets you how many such functions there are. This is a sort of fundamental counting principle, so hopefully that's at least a little bit familiar from a previous class. But even if it's not, I mean, this is, right, don't worry too much about it because we're not going to use this a ton. So in any case, the point is, notice that the bottom, the base of the exponent, is 2, and that's exactly how many elements are here. The exponent is 3, and that's exactly how many elements are there. So this is simply why we chose this notation, is that it kind of represents how you would count up all such functions in the finite case. So anyway, so for anyone who is curious, that's why we use this notation to mean this thing, because it might not have been obvious at first glance. But anyway, okay, so that's what our notation means. Now let's take this notation, let's say that we have a non-empty set X and some field F, it doesn't matter which one, could be reals, could be complex, and let's talk about the space of all functions from, from X to F, right? That's what that means. And I claim that we can easily make this into a vector space with an appropriate definition of plus and times, in fact, a very natural definition of plus and times. So what if I took some 2 functions So if I take some 2 functions from my vector space, this would be the vector space, the scalar field would be the field F, and I am going to define what it means to add these 2 functions together, right? So you give me a function, give me a function, I need to tell you what it means to add those 2 functions together. Well, it's going to be another function. And so since what this is another function, then in order to tell you what that function is, I need to be able to tell you for an arbitrary input what is the output, because that's how you define a function, right? Is tell you what the input and corresponding outputs are. So let's take any arbitrary input from the set X, and I'm going to tell you how to get its output. Well, you just do it coordinate or point-wise, right? So you just take whatever this X is and hand it over to F and hand it over to G, and then whatever the f of X and G of X are, you add them together, and that is the output of the F plus G function. So I've now told you what the function is because I've told you for any given input what is its corresponding output. So that's the definition of plus in this example. You can give a very similar definition for multiplication, scalar multiplication. I encourage you to write down the definition yourself or consult the textbook. I think the textbook is fairly explicit about this. But in any case, you define plus and scalar times in this way, and then you can check that all the vector space properties are satisfied by this example. So this is a nice kind of abstract, slightly weird, but it's an example of a vector space. And it gives you these nice, relatively simple opportunities to exercise these ideas by really sitting down and writing it all out and confirming for yourself that, indeed, my claim is correct that this is a vector space. If you appreciated this content, please like and subscribe. And if there's anything that we discussed here where you'd like to see it elaborated further, I might be able to answer questions in the comments, or for substantial topics, I might make an entire video and add it to the playlist.